Good morning, ladies and gentlemen. It is a beautiful day in 2025, and I'm Munanur Aziza, live from Islamic Senior High School 1, LAMONGAN. Today, we will bring you an important report about fish waste and water contamination in Indonesia. According to the data of the Ministry of Marine Affairs and Fisheries, Indonesia is the one of the world's largest fish producer with a total production of 18.26 million tons in 2023. However, this result is significant fish processing waste, including fish bone, which make up to 11.7% of total waste. Another issue is wastewater from fish processing, which contains high level of ammonia. Now, let's hear to our field reporter, Rama, who will explain more about possible solution. Rama, over to you.
Alright, thank you Una. Now I will explain a solution to tackle ammonia pollution in wastewater. The project namely AWTER, Ammonia Water Filter, focused on creating granulated active carbon from fishbone waste by soaking the ponds in different calcium chloride concentration. This biofilter can effectively reduce ammonia levels in the wastewater. Not only use, the innovation help clean water, but it also add value to fish waste, making it eco-friendly solution. Back to you in the studio. Hi AWTER friends, I'm Rama.
And I'm Muna.
We are from Manila, Islamic Senior High School 1, LAMONGAN.
Get ready for an eco-friendly future, presenting you the production of granulated active carbon from fishbone waste using different calcium chloride soaking variation as a biofilter for ammonia in fish processing wastewater.
As a maritime country, Indonesia produces a large amount of fish waste, including wastewater with high ammonia levels. If not treated properly, this pollution can harm the environment and public health. Clean water is essential for life, but many water sources are polluted by untreated fish industry waste.
Another serious problem is unused fish bone waste. In fact, fish bone have a high carbon content, like a 60% carbon, 25% calcium phosphate, and 15% other organic compounds, making them a good material for water filtration. They can be turned into granulated active carbon to remove pollutants, including ammonia from wastewater.
And then, there are the three problem statements in our research. Firstly, how can fish bones be used as material for producing granulated active carbon with different calcium chloride soaking variation as a biofilter for wastewater from fish processing? Secondly, how does the calcium chloride soaking variation affect the morphology and characterization of granulated active carbon from fish bones analyzed through FTIR, XRD, and SAN? And finally, how effectiveness is granulated active carbon as biofilter is reducing ammonia, COD, and POD levels?
This research focuses on the production and testing process of GHG from fish bone waste. Firstly, the process begins with the preparation of milk fish bone, which are thoroughly cleaned and dried. After drying, the bones are soaked in the calcium chloride solution with varying concentration for 15 hours. Next, the carbonization process, where the bones are heated in the furnace at 350 degrees Celsius for 2 hours, followed by size reduction using a mortar and pestle. Lastly, the activation process is carried out using calcium chloride and sulfuric acid. After that, wash the carbon until it reaches natural pH, and then dry it in the oven 105 degrees Celsius for 3 hours.
To address the second research question, the characterization analysis of granulated active carbon was conducted using FTIR, XRD, and SAN EDX tests. Firstly, test FTIR analysis was performed to identify the functional groups and chemical compounds present in fish bones GIC. The spectrum results show the presence of the main functional groups such as hydroxyl, aliphatic, carbonyl, aromatic, and ester or other in the 1 molar, 2 molar, and 3 molar GIC samples. The most optimal results were of observation at the 1 molar concentration, where the hydroxyl group was found to play a crucial role in wastewater absorption through the hydrogen bonding. Additionally, methyl group were detected under remnants of the organic material, while the aromatic ring, essential part of the carbon structure in the activated charcoal, contributed to stability and atomic properties.
The XRD analysis was conducted through several procedures to determine the crystal structures and compound content in the granulated active carbon. The results show that the ammonia content in the 1 molar GAC reached more than 79%, with a peak area of 82.7%. The functionalization process of activated carbon facilitated the formation of oxygen-containing functional groups on the surface, which made it easier for the ammonia catalyst to attach. Additionally, the size of the activated carbon played a significant role, since granulated active carbon is in powder, so it has a larger surface area, making it more effective in the forming oxygen functional groups that contribute to ammonia absorption.
The same analysis was conducted to optimal GIC after activation with 1 molar calcium chloride to examine support morphology or surface topography of the granulated active carbon after activation. The results shows that GIC with 1 molar calcium chloride activation had larger pores after the treatment. Image analysis using image software indicated that the average pore size before filtration was 38.5 plus minus 2.3 nanometer, while after filtration is turned to 4.0 plus minus 0.9 0.5 nanometer. AWTER was a variation in process due to 5% to 20% error range. This result aligned with the previous study showing that an ideal process is essential for binding both organic and inorganic compounds, including ammonia.
The result of the ammonia content analysis test at the environmental laboratory of Perum Jasa Tirta Malang clearly showed that GAC with 1 molar calcium chloride immersion was the most optimum biofilter. This test provides its ability to drastically reduce ammonia level with a decrease of 83.66 mg per liter, leaving only 0.93 mg per liter after filtration, with an efficiency level reaching 98.9% from initial condition of 84.59 mg per liter. This result is far below the threshold of the good ammonia effluent of 10 mg per liter.
In the same laboratory, we also tested COD and BOD levels. The results clearly stated that the GIC with 1 molar calcium chloride treatment proved to be most optimally as a superior biofilter. In this test, GIC successfully reduced BOD levels by 2,358.9 mg per liter, equivalent to 95.89%, and reduced COD levels by 635.96 mg per liter, achieving an efficiency of 95.28%. This data explains the power of GIC to provide effective and innovative solution in the field of water filtration. This confirms the method's ability to ensure safe water quality.
The result of the ANOVA analysis also showed that the null hypothesis was accepted because the calculated F value was smaller than the F table. However, there were significant differences between the variable tested COD, BOD, and also ammonium. And the treatments applied GAC 0 molar, 1 molar, 2 molar, and 3 molar. This indicates that the application of the calcium chloride variant of GAC has a significant effect on changes in the COD, BOD, and also ammonium values. In conclusion, first, the fish spawn waste can be used as a product, granulated active carbon, with different calcium chloride sodium variation like a 1 molar, 2 molar, and 3 molar. Secondly, characterization tests of FTIR, XRD, and SAM show that 1 molar calcium chloride GAC has an optimal structure, with an over 79% of ammonia. And finally, the third is GAC from fish spawn is an effective biofilter. This 1 molar calcium chloride variant gives the best result. Why? Because it reduces ammonia by 98.9%, also significantly lowering GOD and BOD. With passion, we create.
With creation, we innovate.
With innovation, we solve it. Thank you.